Okay, thank you everyone again for joining in for the next in the series of lectures. Today I thought we would, I'm going to start by asking a question that in some sense seems unrelated to the information paradox, but hopefully by the end of the lecture, the relation to the information paradox will become clear. So I'm going to ask the following question today. Okay. I'm going to ask how close are pure states to mixed states. Okay. And in fact, for most of the lecture, I'm just going to discuss some elementary statistical mechanics. I have to, of course, explain many terms in this question. What does close mean, and so on. I'm going to, for most of the lecture, we are just going to discuss some simple statistical mechanics. This is a fun discussion. In any case, maybe some of you are familiar with it, but if you're not, this discussion that we are about to have in this lecture is like a useful discussion because it applies in many situations. It's useful when one thinks about thermalization, and I mean it's useful in many contexts, also in the context of black hole information. But the relevance of, at the end of the discussion, the relevance to Hawking's original paradox should be quite clear, and I'll try and make that clear. Before I start the discussion, I realized that yesterday there were some questions even about pure states and mixed states. So let me just start by giving you a very quick review of the difference between pure states and mixed states, and the sense in which we are using them here. So in quantum mechanics, there are two sources of uncertainty we can have. Okay, one is the thing that is drummed into us as undergraduate students, right? We have the fact that quantum mechanics, when you make observations, those observations are inherently probabilistic. And there's a famous example of this, which is the Schrodinger Cat State. Let's make a cat. Okay, so we can have a cat, and so you can have a state which is a state of this kind. Okay, we don't want the cat to be dead, but let's talk about a superposition of an unhappy cat and a happy cat. Okay, so we can have a state of this kind. Right? This is in principle, a possible state in quantum mechanics. With some coefficients a1 and a2, provided mod of a1 squared plus a2 squared is equal to 1. Okay, so there's a superposition of a happy cat and an unhappy cat. And if you were to observe the cat, then you would find with probability a1 squared that the cat is happy, and with probability a2 squared that the cat is unhappy. Okay? But of course, there is the usual classical uncertainty you could have. And so there is something that could have happened even just in classical mechanics, where you might have had some uncertainty about the state of the cat. Right? So this is what's called a pure state. But we might also have what one could call a classical mixture, where with some probability a1 squared, the cat is happy, right? And with some probability which is a2 squared, the cat is unhappy. Okay. So in this situation, this is something which could just happen classically, right? There could be some, maybe you toss a coin. The coin is a biased coin. It sometimes gives you heads if you get, it gives you heads with a1 squared and tails with a2 squared. If you get heads, you feed the cat some milk, so the cat is happy. If you get tails, you don't feed the cat some milk, so the cat is unhappy. And so, that kind of situation would lead to a classical mixture where, once again, there was some uncertainty in what the cat was doing, whether the cat was happy or not. But notice that these two states, if I call them 1 and 2, are not actually the same, and they are distinguishable. And they're distinguishable in a pretty straightforward way.
Yeah, there was somebody's mic not muted.
Yeah, so could you just mute?
Yeah, it's
fine. Okay, thanks. Okay, so so there's these states are distinguishable in some pretty simple way, and that is that and the way you distinguish these states is if you take this state. I'm not going to draw cats again, but let's say you have a two-state system, and you take the state which is this plus a2, and 1 and 2 could be qubit states or states of a cat or whatever. You could then ask, what is the expectation value of some operator A in the state? And the expectation value of the operator A in the state is given by, I mean, this is just a trivial computation. It's given by you know, a1 squared into the matrix element of this operator A in the state 1 plus a2 squared and the matrix element of the operator A in the state 2. But very importantly, there are additional cross terms that arise, and the cross terms that arise are a2 star a1, okay, into 2a1 and plus a1 star a2 into 1 a1 star a2 into 1a2. Okay, and these cross terms do not arise, these terms which we have here do not arise in the classical situation. Okay, so this pure state, which also seems to have some uncertainty in the state of the cat, is different from the state where you have a classical mixture. Okay, in the case where you have a classical mixture, if you were to compute the expectation value, you would just get this. There's some probability that the state is 1, there's some other probability the state is 2. You compute the expectation value of some observable, and you look at what the value of the observable is in state 1, what the value is in state 2, and you just add it up with the probability that you're in state 1 and state 2. And I emphasize that this term which appears in the first case does not appear in this case. So these terms are identical, you'll see, and then there are additional terms that appear. Okay? So the classical mixture is usually represented, the second situation we're talking about, is represented by a density matrix, which in the case we've been talking about would be this density matrix. Okay. And if you want to compute the expectation value of some observable in this density matrix or in this state, this is also called a state. I mean, when people use the word state in quantum information, they are not necessarily only talking about pure states. They're talking about, you could have a state of the kind here that we have written here, or you could have a state which has some uncertainty of the kind that you have here. And the way you compute an expectation value is just you take trace of rho A, and that indeed would give you the expression that we have on top. Okay? This density matrix that I've written down here is a density matrix of a mixed state, which is different from the pure state, which is represented by the wave function that we had above. Of course, you could take the pure state and you could write a density matrix for the pure state as well, which would just be psi psi, and you could compute expectation values in this pure state density matrix as well, psi psi. So there is a density matrix which corresponds to the pure state as well, which is a different density matrix, which is this. And once again, the rule for computing expectation values is again that you do trace of rho pure into A. It's not a different rule, but you'll get the answer that's written on the top of the blackboard and not the answer that's written below. And notice that this pure state density matrix satisfies an important property, which you can see from the fact that it's psi psi, which is that rho squared is equal to rho. Okay? And this property is what distinguishes this pure state from this state, okay? From this mixed state. Okay, so that's what we mean by a pure state and a mixed state. And the objective of today's lecture is to kind of ask almost an inane sounding question, which is how close are pure states of the kind we have on top to mixed states of the kind that we have in the middle of the board. Okay, we want to ask this question in a slightly more refined setting, not just in the setting of two state systems. So let me add a little bit of physics to this situation. So let's say we have some system, and the system has some energy levels, and I say I only want to consider energies which are about some mean, which is E0, and so there's some mean energy, and there is some spread in the energy. Okay, there's some spread. In general, this spread is much smaller than the mean. Okay, so we will always consider the situation where the spread is much smaller than the mean. So you have some mean energy, but the energy is not exactly fixed, and you have some spread in the energy. And I want to now draw states from this set of energy eigenstates that live between this range E0 minus delta to E0 plus delta. Okay? So in general, I could draw some state which had, which was a superposition of these states. So I could consider a state of the kind AI EI, where this I in general could run from 1 to some number that we'll call W, and this W is the number of energy states, is the number of eigenstates in the interval of interest. Okay. So this is the number of eigenstates. This is just notation so far. But of course, you know that this W, there's some physics associated with this W. And this W, in fact, is nothing but the exponential of what we would call the entropy, which tells you how many eigenstates there are in this interval E0 minus delta to E0 plus delta. Okay? So this is an example of a pure state. It's a pure state. It's a superposition of energy eigenstates. And it's, you just take some superposition with some coefficients AI. Of course, the coefficients AI need to satisfy sum of AI square is equal to 1. But other than that, you could pick any coefficient subject to this constraint, and that would give you a valid pure state, which is picked between these two energy ranges. Okay? But in fact, when we usually do quantum statistical mechanics, if you in graduate courses on quantum statistical mechanics, we don't usually consider states or pure states of this kind and try and ask what their properties are. We consider a particular mixed state. And the particular mixed state we often consider, we often consider a thermal state as well, but there's another commonly considered state, which is the density matrix, which is this density matrix. Okay? So this density matrix is a classical mixture of these different eigenstates, and it has to be correctly normalized because, the probabilities have to add up to 1. This density matrix is the microcanonical density matrix. And what this density matrix is doing is it's saying that, you have a system. The system can be in one of these energy eigenstates, which range from E0 minus delta to E0 plus delta. There's an equal probability for it to be in any of these energy eigenstates. That probability is just given by 1 over W. We know that the probability has to be 1 over W because the sum of all probabilities has to be 1. There is no probability for it to be above energy E0 plus delta and no probability for it to be below energy E0 minus delta. Okay? So this is a microcanonical density matrix, which is what we usually use to discuss quantum statistical mechanics. Of course, we often also talk about the thermal density matrix, but as you know by the equivalence of ensembles, the thermal density matrix is close to the microcanonical density matrix. So for this lecture, I'm going to discuss the microcanonical density matrix because it's slightly simpler to discuss. Okay? So what I want to now ask now is how close is the state psi that I wrote? Okay. Is psi, which is AIEI, to rho to this microcanonical density matrix. Okay. Now, at first sight, you might say, what does it mean to ask how close psi is to AIEI? These are distinct states in the Hilbert space. In fact, if you were to try and define some norm on the space of density matrices, this state psi is completely orthogonal to this microcanonical density matrix. But I'm going to try and argue that in a sense, if you take typical states, okay, the typical state psi, and I have to explain what typical mean. Typical state psi are extremely close to this microcanonical ensemble. Okay. Now, even though, as I just argued to you, it's clear that these are distinct states in the Hilbert space, I'm going to try and argue for this result. Okay. There are two words there are two phrases I need to specify. I need to explain. One of them is this phrase typical states. I haven't told you yet what typical states means. And second, I need to explain what extremely close means. What does it mean for one state to be close to another state if the states are orthogonal, right? Usually when we talk about orthogonal states, we say, there's some state which is a spin down. It's orthogonal to a state where the spin is up, and there's no sense in which these states are close to each other. Okay? So I have to explain what these two terms are, and I'm going to now explain what these two terms, close and typical states, means, and I'm going to try and establish this result. Okay.
Yeah,
okay.
Suvrat, there's one question. He's asking, so all mixed states are classical in nature?
All mixed states are classical. No, a mixed state is a classical, you see, in the mixed state itself. So let's look at this. When you look at this mixed state, this says that in the mixed state, you have some classical probability to be in one energy eigenstate. In addition, if you were to make an observation, the way you need to ask what the result of the observation is, of course, you could have, you you'd find yourself in one of the energy eigenstates. But even within that energy eigenstate, there could be quantum uncertainties in certain observables. Okay? So mixed states are not classical in nature. Mixed states are classical mixtures of quantum states. So, it's a case where you have a classical uncertainty in addition to the quantum mechanical uncertainty that you always have. So a mixed state is just one where, you have a state in a box. That state is a quantum state, so it has whatever quantum uncertainties are there. But in addition, you don't know which state you have in the box. And when you do statistical physics, you say, there's this room. The room has various energy eigenstates. Those energy eigenstates have various quantum fluctuations. But we, in addition, say, when we say the room is thermalized, we say, well, it's good to assume that the room could be in any of its energy eigenstates with uniform probability. And this is supposed to give you good, sensible answers for statistical physics. You could ask for a different density matrix where you could say the probability is proportional to e to the minus beta e, and that's the thermal density matrix. And that's another density matrix which is supposed to give you good answers for statistical physics. Okay.
Sorry, I have a question.
Yeah.
So this rho micro is the density matrix for a mixed state, right?
Yes.
So what did you mean by saying that these two states are orthogonal to each other in Hilbert space?
Yeah, you could try and define there is some observable which will give you 1 in the pure state, and which will give you 0 in the micro state in the microcanonical density matrix. So these states are distinguishable. When that happens, they're orthogonal. So you could try and define some norm on the space of density matrices, and these states are distinct states. They're not in any sense the same state. There's one notion of close, which is where if you take two wave functions and the wave functions have a very large overlap, then you'd say that the states are very close, right? If you take like the state which is up and you take the state which is 0.999 up plus 0.0001 down, those states are close. And they're close in the sense that, there's no observable, there's no observation you can make in which the probability distribution of the observation is significantly different in one state and in the other state. Okay? So there's some distance you can define. There's a norm on the Hilbert space. In this situation, this is not the case. You can find observables which clearly will distinguish for you these two states.
So when we talk about, for instance, mixed states,
yeah,
right? So we talk about a full pure state in a Hilbert space, and then we sort of integrate out part of it to get the mixed state, right?
You could think of it that way. In this situation, yes. You could. I mean, in all situations, yes.
I mean, then that pure state. All the pure states of which part we integrated to get this mixed state, we can try to find their inner product with this pure state that you're considering, right? And
yeah, it would be close to 0, because you see this mixed state. First of all, there's no unique purification, but you could try and purify this density matrix by introducing an auxiliary system, which in this case of this room could be the world outside. And you could write down a purification, which was where the energy eigenstate in this room was entangled with the partner state outside. And in the case of the pure state, there's just no entanglement between the state in this room and the state outside. So in one case, you have a product state. In the other case, you have a state which is maximally entangled between this room and outside. And so that inner product, you could compute using the bond rule. It would be 0.
Right. Yeah, thank you.
Okay. So great. So now we want, but so I just tried to explain to you why these states are orthogonal. So what does it mean to say that they are close? The point is we want a physical notion of closeness. Okay. So we want a physical notion of closeness. And in particular, the question we want to ask is, let's say we have some observer. This observer can make some observations, right? So from the point of view, POV is just point of view of physical observations, how easy or difficult is it? Easy or difficult is it to distinguish the two? Okay. So as I said, there is, and so this is a more physical notion of what one means by close. Okay. In that, it could be that this room is in some sense disentangled from what is happening outside, but it might still be very hard for me inside the room. I mean, maybe in this room I'm large compared to the room, but if I were to disentangle this entire city of Bangalore from its surroundings, it would still be very hard for me sitting here to make observations that distinguish now the state of Bangalore from the state, where Bangalore is entangled with everything else as it is in our real world. Okay? So the question we want to ask is, if you are an observer making physical observations, how easy or difficult is it? And we'll make this a little bit more precise. Okay. So how do we make this a little bit more precise? Remember that in quantum mechanics, what is the physical observation that you can make? Okay, so physical observations always have to do with projectors. Right? Physical observations are basically the probabilities of different outcomes, right? And the probabilities of different outcomes are given by taking P, a projector P, okay, and by asking, what is the expectation value of this projector P in the state psi? Okay? And that's the most general kind. I mean, you can make more general observations, but this is a very general kind of observation that you can make in quantum mechanics. Okay? And the physical significance of this observation is that, let us say you had some observable O, which was a Hermitian observable, whose spectral decomposition looked like this. So maybe there are some other projectors, and this observable always has some spectral decomposition. Then what this expression that we have written down here is telling you is, if one measures O, okay, upon measuring O, what is the probability of getting lambda? Okay. Now it's important that the information is not actually sitting inside lambda. Okay. People often say, and I mean, it's in some sense, it's convenient not to always talk about projectors, but people often say, let's just compute the expectation value of O, and the expectation value of O not only knows about this probability, it also knows about this eigenvalue lambda. Okay. But it's important that actually the physical, when we talk about whether something is easy or hard to measure, the physical thing that you measure is always the probability distribution. And the reason for that is that, if you just, you could always say that I don't want to measure O, but I want to measure like 1000 O, right? I'm free to do that. I'm free to say that I rescale my, whatever answer I get, I just multiply it by 1000. Now, obviously, there's no physics in that, but this kind of process takes all these eigenvalues to 1000 lambda, right? But that doesn't make, just because you chose to use a different unit or you chose to use some different units, can't possibly, make the state easier or harder to distinguish from another state. And the key to that is that, even though you rescale O to being 1000 O, you did rescale these eigenvalues lambda to being 1000 lambda. But of course, the probabilities are invariant under any such rescaling. Okay, so it's useful actually, in these discussions to talk about probabilities. One could talk about observables and expectation values of observables, but you'd have to be careful to fix a normalization of the observables ahead of time, because otherwise you could always say that I can always distinguish two states by just measuring like 10 to the 10 times some observable. And even if you have two states which are very close in that they're almost parallel to each other, you could always find some expectation value whose difference would be order 1 between the two. But that's not really something physical. And the reason it's not something physical is because, if you were to measure probabilities of getting different outcomes, those would be almost the same. Okay, so that's why it's important to talk in terms of probabilities, or alternately in terms of normalized observables, but we'll speak in terms of probabilities, which is easier. Okay? So what we want to ask is, if you have a typical pure state, and I have not yet explained what typical means, have a typical pure state and some projector P, then I can ask, how does this expectation value compare with the same expectation value computed in this mixed state where this rho is a micro mixed state. Okay. So this is now a more physical notion of what one means by closeness. Okay, it's the fact that one is making an observation, and one gets some probability distributions for the observation, and one is asking, how does the probability distribution in the pure state compare with the probability distribution in the mixed state? And this is really now making contact with something physical, where because this is a question that one could ask and try and answer. Okay? Now there is yet another term that we have not defined, and the term that we have not defined here is what one means by typical pure state. Okay? Given a if I were to give you a particular pure state, I was to tell you that I want to consider the state where the first energy eigenstate is multiplied with the coefficient 0.3, the second one with 0.25, and third one with something else. You could compute for me, and given a certain projector, you could compute for me what the differences of these probabilities are. But we don't want to ask that, right? Because we don't want our answer to depend on which particular pure state we are comparing. And so we want to have some notion of what one means by a typical pure state. And so the next thing I want to do is explain what one means by a typical pure state. Okay. So let me just remind you a little bit about the structure of the Hilbert space. Remember, I said that one could pick any state subject to the constraint that sum of mod of AI squared is equal to 1. Okay. Now, because there are actually W of these AI coefficients, remember, one way to think about this is that you have some state, and you can rescale all of you can think of these as rays in some complex projective space. So you could think, it is more accurate to think of the Hilbert space as a copy of the complex projective space with W minus 1. Okay? But for simplicity and just for the sake of visualization, one way to think about the state is to think about it in terms of just a sphere. Okay? So you just have a sphere, and the Hilbert space, if you think about it geometrically, it's of course a sphere in very high dimensions. But the Hilbert space consists of just picking points from the surface of this sphere. Okay, so you have some sphere, and you have to pick points from the surface of the sphere. Let me remind you that when you say that sum of AI squared is 1, that doesn't completely identify a state, because we have not yet modded out by overall phase ambiguity. These states are actually identified, psi and e to the I theta phi. And that so if you have some configuration of AI and you rescale all the AIs by a phase, that's actually physically the same state, but we don't have to be careful about this ambiguity. So we'll just consider states as being defined by giving a certain set of complex numbers subject to the constraint the sum of AI squared is 1, and we won't worry about this phase redundancy. You can do it more. You can do the entire analysis more carefully by worrying about it, but it will not be important in whatever we do. Okay. So the question now is, let's say we have this sphere, we have the surface of the sphere where where we have all of these states, and now the question is, if one picks a point at random. Okay, so pick a random point on the sphere, and then ask the question that we asked, right? How close is, how does psi, so a random point on the sphere corresponds now to a state, a given pure state. And given a random point on the sphere, one can ask, how does this compare to trace of rho p? Okay. So now I've reduced my problem to specifying what one means by random, and specifying, in fact, some measure or some volume measure in the sphere. And the way I'm going to define random is I'm going to specify a volume measure in the sphere. And I'm going to say I just pick a point in the sphere with equal probability. Okay, so I'm picking. So now there are many probability distributions in the game, so you shouldn't get confused. In this situation, what I'm saying is, it's like I go to the market and I buy a pure state, and I could get any pure state I wanted, but in the end, I will have a pure state. Okay? So I want to now, I want to pick a state with this probability, with some probability, and then compute expectation values in the state. And if you did that, you could ask, what is the natural kind of probability distribution you could put in the state? Remember, by the way, when I'm picking a state from the sphere, I'm not picking over orthogonal states only. I'm saying, I have a sphere, and from the surface of the sphere, I'm picking some state. And that's what I mean by a notion of a typical state. And the way one can make that more precise is by defining a measure on the Hilbert space. And the measure is defined as follows. And this is the natural kind of measure you would put in it. And this is now a measure on this Hilbert space. The reason you have D2A is because these are complex numbers. Okay. This delta function is imposing for you the normalization of the state. And this factor is just a factor. It's another normalization factor that's just there to ensure that integral of d mu psi is equal to 1. Okay. So I want to pick a pure state at random. And when I pick a pure state at random, of course, when I say random, I have to have some notion of, my probabilities have to add up to 1. And so I'm picking a pure state at random, and this V is meant to ensure that, my probabilities all add up to 1. Okay. So this is this is my definition of what I mean by a typical pure state. And the question I want to ask is, let's define this quantity which we'll call delta. So we are given a projector, and we can define for any given state this quantity that we call delta. And we can ask, let's say the world happened to be in some particular pure state, or the system happened to be in some particular pure state. You can ask questions like, what is delta with this probability distribution mu? What is delta squared with this probability distribution mu? And similarly for higher order moments of delta. And that is what we would like to compute. Okay. I should say that this V you can compute explicitly. It's not hard to compute. It just happens to be 2 pi to the W by gamma W. So this V is just something one can compute explicitly, and this ensures that the probability distributions add up to 1. Okay. So I hope the objective of what we're doing is clear. Let me just reiterate. I have this space of pure states. There's an infinite number of pure states because I could pick the coefficients in some continuous way. Now I'm saying I want to now ask, if I pick a state at random in this space of pure states, how close do I expect it to be to the microcanonical mixed state? And closeness is being defined by using this notion of a projector, because that projector corresponds to the probability of getting outcomes in a certain measurement. And so there's a physical notion of closeness which corresponds to experiments that someone might do. And there's a notion of typical which is defined by this probability distribution. And we want to compare now these pure states and these mixed states. So before I go on and I do some calculations and I tell you the result, I wanted to ask if what we're doing is clear, and maybe stop here for questions and see if there are some.
Yeah, actually, I think Tunir has a question. He's asking, P is the projector on which space?
Yeah, we have not specified that. P is just a projector which appeared here. It's just something that appeared in the spectral decomposition of some operator. So it's the projector onto the eigenspace of O, which has eigenvalue lambda. So P is a projector. I mean, I'm just using projector as a shorthand for a possible outcome of a physical measurement that you could do. And all possible outcomes are specified by projectors, and that's why I'm using a projector. I'm not saying it could be any projector you like.
Right. So the notion of nearness that you will define is operator dependent.
Good. So let's say good. So we'll have something a little bit more to say about that. In the end, the notion with the result will not be operator dependent because in the end the result we have will not be operator dependent. But you're right that right now for a given question, if when I ask. If I ask this question, it might look that the final answer depends on what P is, but in fact the punchline or the main part of the final answer will not depend on what P is specifically. But you're right, of course. If I give you a given state and a given and a given projector, there is some notion, there's some distance between these two quantities we have on the screen, this one and this one, and that depends on the state and on this particular observation we are doing. But in fact, the nice part of the result we are going to get is that it's not going to depend on which observation you make. It's going to be true for all kinds of observations. But you're right, at this point, it might appear that it does depend on the observation.
Suvrat, I have a question.
Yeah.
You're picking the state psi randomly, as in according to some uniform probability distribution on the Hilbert space?
Yes. This is the probability distribution. So this is the probability distribution I wrote down. This is So this is a uniform probability distribution in the Hilbert space. It's actually the Haar measure in this Hilbert space. Notice that even though I wrote down this distribution in terms of these variables AI, this is actually invariant under change of basis. You might have said it looks like you've privileged somehow these AI coefficients. What if I chose to use a different basis where I chose to use E1 plus E2 and E1 minus E2? You can check that this measure, the way I've written it down, is invariant. It's invariant because under unitary transformation of the AIs, this delta function will be invariant, and so will this measure D2AI.
Okay, thank you.
Good. Are there any other questions about the physics of what we're doing? I think this is kind of just an important conceptual point. What I want to say is, here's another way to say it. What we're saying is, we're in this room, we don't know or let's say you're given a state, but the state was produced, this pure state, there's some quantum computation that is produced for you a pure state, but it was a very complicated quantum computation. So you don't know what pure state it produced for you. And then you want to ask, to what extent is this pure state that you have close to a mixed state or not with respect to this physical observation? Of course, as we said, given a particular state, there is always some physical observation that will clearly distinguish it from a mixed state. But the question we want to ask is, let's say we ahead of time, wanted to make some physical observation, and this quantum computer produced a state for us. What are the kinds, how much do we expect this physical observation to be different from the same observation carried out in the microcanonical state? Okay.
Actually, Suvrat, there's one more question.
Yeah.
He's asking, is this, one second, is this measure also independent of the phase ambiguity?
Yeah, the measure clearly doesn't involve the phase. Yeah, it's a D2 AI. So, if you rescale A's, yeah, it doesn't involve the phase. And there's a delta AI squared. We're kind of overcounting states a little bit because, we're counting AI and we're also counting AI into e to the I theta. So there's a 2 pi overcounting that we're doing, but it's not going to matter in anything we do. Okay, great. So the first quantity we want to compute is just the expectation value of delta, right? So let's just compute what is the expectation value of delta. Remember, this delta is the difference between the answer you get in a pure state and the answer you get in a mixed state. Okay? So what is, given a particular state in the Hilbert space, what is just this expectation value? Let's just write it down. So this happens to be mod of AI squared into EI, P EI. This is this projector. And then there are off-diagonal terms, which are terms where you do not have I equal to J. And these were the terms I emphasized at the beginning were important for distinguishing. I maybe got my, let's put EJ here. These were the terms I emphasized in the beginning were important because they distinguished a pure state from a mixed state. In the beginning of this lecture, I wrote down these terms and I said, look, these cross terms don't appear when you have the mixed state on top. But they do appear in these pure states. Okay, so now we have, this is what this expectation value of P is in a given pure state. And what do we need to compute? Well, we need to average this over all possible pure states using the probability distribution that we wrote down. So what we need to compute is the average of this, using the probability distribution, which I'm calling mu, on this space of states. Right? Now, what do we need to compute this average? We need two quantities. We need the expectation value of mod of AI squared with respect to this measure. And we need the expectation value of AI AJ star with respect to this measure. This d mu psi, I remind you now once again, if you've lost track, is just this measure that I'm writing here. The reason there's a subscript psi is because it's a measure on the space of states. And it's a very simple measure. It's just the product over all of these coefficients with this delta function constraint put in. And V is some factor you can work out, but you can forget about it in the course of this lecture. If you do any computation, you'll have to keep track of it. But it's just something which is allowing you to vary overall coefficients with a delta function for normalization. So the question is, what do you expect these two answers to be? The answer for mod of AI squared and the answer for AI AJ star. So notice this is actually pretty simple to work out. The reason it's simple to work out is that this expectation value of AI squared when I say expectation value, I mean expectation value with respect to this measure clearly cannot depend on I, right? It cannot depend on I because our measure was completely symmetric. It wasn't treating one I differently from another I. So it cannot depend on I, right? It does not depend on I. And, so it must be the case that, you can just as well compute sum of AI squared and divide it by W, and that has to be the same as the expectation value of AI squared mu. But sum of AI squared has to be 1 because that's a constraint, right? So this must be the same as AI squared mu, but this must be 1 over W. Okay? You can, of course, just do the computation using the probability distribution, but this is a shortcut to get the answer, which tells you that the expectation value of every coefficient of all of these states is, the expectation value of the square of every coefficient is 1 over W. So the physical meaning of this is, it's a very simple result. It's a statement that, if you were to pick a random, let's say you pick a random state, which is a superposition of all of these energy eigenstates. And I ask you, what is the norm of the coefficient? What is of the 10th energy eigenstate? Right? And the norm of that coefficient is 1 over W. It's obviously just e to the 1 over e to the s, where e to the s is the total number of states. Right? Because the norm of all coefficients has to be the same, and the only way you can, get normalization is if all the coefficients are approximately of size 1 over e to the s by 2. Okay, so that the square is 1 over e to the s. So this is a pretty simple and intuitive result, and you can also see that AI AJ star must be equal to 0 when I is not equal to j. And that's pretty obvious. It follows from the fact that, if I fix a value of ai and I sum over aj, then of course I'm allowed to have, for a given value of ai, I can also take the configuration where I just take aj to be minus aj. So if I say, the question here is, let's say I give you a pure state at random, and I say, what is the correlation between the coefficient of the first energy eigenstate and the correlation of the coefficient of the fifth energy eigenstate? There is no correlation, because the phases of these states are completely random. When the first energy eigenstate has some positive phase, this thing could have entirely the opposite phase, and therefore there is no correlation, and therefore this correlation is just 0. So both of these are like simple and obvious kinds of answers. And so this tells you that if you were to compute this expectation value, it happens to be 1 over w into sum over I ei p ei. Okay. This is the integral with respect to this probability measure. Okay. But this expression that we see here is a familiar expression. This expression is exactly the same as trace of rho p, where rho is 1 over w into ei, right? Where rho is the microcanonical density matrix. So you see that the average, or the expected expectation value, so this is an expected expectation value of any observable, if you were to pick a random pure state, is exactly the same as the microcanonical expectation value. Okay, so this is the first result, which is kind of a simple and nice result that one can get, but it's nevertheless an important result. And it tells you that even though in general for a given pure state you compute the expectation value, it will not be the same as the microcanonical expectation value, because it might be that in a given pure state some coefficients are larger and some coefficients are smaller, and in addition there are these cross terms that you need to worry about. If you were to ask, if you have a random pure state and someone was to ask you to take a bet on what the expectation value of this projector would be, you would be best off by taking a bet on this expectation value, which is just the microcanonical expectation value. Okay, so this is the first result that one can compute. Now perhaps some of you are thinking that the way we derive this result is by arguing that the reason all of these deviations from the microcanonical expectation value cancel out is because maybe there were positive and negative deviations. As you see here, we said that these cross terms average to 0 because there are positive and there are negative deviations. And indeed it could be the fact that the average deviation from the microcanonical expectation is 0 may not be so surprising, because you could have said well, okay, maybe the average deviation is 0 because sometimes the deviation is positive, sometimes it's negative. But in fact, pure states in general have large deviations. They have either large positive deviations or large negative deviations. And the reason you're finding that here, and what we found here, is that the expectation value of delta is 0 is because it doesn't say anything. Maybe delta actually has a probability distribution which is just bimodal and can be very large. So it's important that this does not end the story. And we in fact also need to compute the expectation value of delta squared, okay, with the same probability distribution. So the expectation value of delta squared tells you a little bit more. We already know that delta is distributed around 0, but the expectation value of delta squared now tells you what is the typical size of fluctuations in the pure state away from the microcanonical mixed state. Okay. So delta squared is a computation that one can do. It's a slightly harder computation, but we can do it, and and here's how one does it. You see this delta squared. Let's just try and do it, and I'll sketch the computation. The way that if you were to compute what this delta squared is, you would do the computation this way. You would say, well, let's take this. This is delta. Let's square it and let's integrate it over mu. This is the definition of delta squared. Okay, now let's expand out all of these coefficients, all of these terms. So if you were to expand out all of these terms, you would find what you're computing is a sum over, there are 4 terms in the sum over these different energy eigenstates, and you're computing ei p ej into So I messed this up in my notes. I realize into AI AJ star minus delta IJ by W. This is the term that's coming from the trace row. And then you have an EK PEL. And I have again messed this up. EL EK AK AL star minus delta KL by W. Okay, and I have to integrate this. I hope you see, all of you see why you get this expression when you expand this out. You know, you're going to take psi p psi, and you're going to minus trace of rho p, and you're going to multiply it with itself. In this expression on top, you see here psi p psi, and there are these coefficients which are AI AJ star multiplied with PEI EJ. So you see these coefficients. This is psi p psi. This is trace of rho p. Right? Trace of rho p only knows about, you know, it's just tracing with the coefficient of 1 over W. So that just sets I equal to J. That's why you have a delta IJ here. And so this term is trace of rho p. Okay. And on the second line, I've written the same expression because I'm squaring it. Okay. And this expression is a real expression because it's the expectation value of some Hermitian operator. And so I'm just squaring the expression. And so I have the same expression written on the first line and the second line. And I just have to do this integral. Okay? Now, when you do this integral, you will see that you will get 4 different terms. Okay, you will get terms which are AI, AJ. So the main thing you need to compute, the integral you need to do is this integral. Okay? AJ star AK AL star B mu. Okay. Now, this integral is something one can do. I won't do it right now, but let me just write down the result. It's a simple integral, which just involves, you know, doing some simple integrals with this Haar measure that we wrote down. You have this Haar measure, and now you have some coefficients. You have to integrate with you know, it's not just the integral with the delta function, but with some polynomials written in front of the delta function. And you can check that this integral turns out to be the following. It forces either I equal to J and K equal to L, which you expect, or it forces I equal to L and J equal to K. And the whole thing doesn't depend on what the values of I, J are, as of course you expect it will not, and it's W into W plus 1. Okay. So this is kind of, you know, the tensor structure that you get on top is kind of simple and expected. It has to be the case that either I was J or K was L, and K was L, or I was L and J was K. Because otherwise, you know, it's clear you would get 0. And then, you know, there's some coefficient which you compute by doing the integral, and that's just W into W plus 1. Now, you can persuade yourself that when you expand this out, you see that these delta functions, these Kronecker delta functions as well. When you expand it out, these Kronecker deltas will give you a contribution which is delta IJ, delta KL, if you see when you multiply these two out. Okay. So delta IJ, delta KL is when this is equal to this and this is equal to this. Okay. You can persuade yourself, I won't do it right now, but it's, if you work this out, you can persuade yourself that in fact the contribution, so that's this contribution, the expression, this delta squared, is bounded above by the coefficient of this term, the second term, because the coefficient of this term is something negative which multiplies, you know, which gets cancelled off by the minus signs from here. And therefore you only need to worry about the coefficient of this term. And so let me just tell you what that coefficient is. So you see, you will find that delta squared is smaller than 1 over W into W plus 1 into EI PEJ into EJ PEI. Okay, and you have to sum over all I and J. Okay. This 1 over W into W plus 1 came by doing this average with this probability distribution. And remember, I said there was one delta function which contributed. I've inserted that delta function. That delta function sets these indices to be pairwise equal. The way this delta function works is it sets these intermediate bra and ket states to be pairwise equal, and these outside bra and this ket to be equal. Okay. But now look at what this expression is. You see, what is this expression? In the middle, you have a sum, you have P, and you're summing over what is almost a complete set of energy eigenstates. It's not a complete set of eigenstates because, you know, we have restricted ourselves to some range of energies in the Hilbert space. You're not summing over all energies in the Hilbert space. And therefore, this is smaller than just computing the expectation value of P squared in EI. That's because P is a positive operator. And so I could have added these additional terms, the additional states which are missing in this EJ, and that would have given me P squared. But remember that P is a projector, and therefore P squared is just P. Okay. So this is just the trace of P. But what can the trace of P be? You see, the trace of P, Tunir asked sometime back, what was the projector we were looking at? What space was it projecting onto? What is the largest projector we could have? What is the largest expectation value we could have for the trace of P? It cannot possibly be more than W, right? It has to be, even if P was like just the identity operator on a microcanonical space, even then the trace of P would at most be W. And therefore, this is smaller than 1 over W plus 1. Okay? What it is exactly depends on what P is. But in general, for any projector, even for the largest possible projector, this delta squared is smaller than 1 over W plus 1. Okay? So we have found that the expectation value of delta squared is bounded above by 1 over W plus 1. Okay? Now, you might have thought, we're doing all this algebra with these probability distributions, and what does this have to do with any physics? But in fact, if you just think about this, this is actually, it's such a simple result, but it's a significant result. And the reason it's a significant result is that, remember, that W is e to the s, right? So what is the fact that delta squared is 1 over W plus 1 telling you? It's telling you that average deviations, are of size square root W, and therefore they are of size e to the minus s over 2. And so it's telling you that not only is it the case that pure states on average look like the microcanonical density matrix, if you were to just take the deviation of pure states from the microcanonical density matrix and square it and average it over the entire Hilbert space, you would find that the average deviation is e to the minus s over 2. Okay? And that is a very small number, and that's already telling you that on the whole, pure states or typical pure states look a lot like the microcanonical mixed state. Okay? In particular, let me just emphasize that this is telling you this result has two parts to it. It is telling you that for a given observable, okay, for any observable, most pure states, where most is defined by states which occupy most of the volume in the Hilbert space, most pure states look exponentially close to the maximally mixed state, close to the microcanonical state, which is the maximally mixed state. And secondly, you see, it could be the case that there are some observables for which, for any given pure state, we said at the beginning that you could always find an observable which would clearly distinguish for you the pure state from the mixed state. But the volume, and let's say the volume of atypical states, another way to say that is if you're given an observable, there is some state for which, that observable will just give you 1 in a pure state and give you 0 in the mixed state. But that state is what one might call an atypical state. The volume of atypical states is exponentially small. Okay? And this result follows from the very simple observation that you compute this delta square, you define it correctly, and you find that it's 1 over e to the s. Okay? And there are two parts to this. The only way this could happen is either the delta is small on most of the Hilbert space. It's smaller. It's like 1 over e to the s by 2. And that's why you're getting, that's the first part. So that's consistent with this. It could be the case that maybe for some parts of the Hilbert space, delta is large, right? There are some parts of the Hilbert space where maybe delta is 1. The pure state looks very different. Some pure states look very different from the mixed state if you're given one observable. But the volume of such atypical states is exponentially small. The moment you go slightly away, you start looking at slightly different states. If you're not sitting right on top of that atypical state, you again find that you're back to typicality and things just look maximally mixed. Okay, so there's a graphical way to say this. Let me just say, here's a way to say this. It is that, if you think of the Hilbert space, maybe I should use a different color. Oops, that's also not good. 1 second. Orange. Okay, I don't know how clearly you can see that, but this is my Hilbert space. This is and in this Hilbert space, you know, the atypical states, okay. The atypical states are like some very, 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 very small parts. You know, they occupy some very, very small volume on the Hilbert space. And most of the Hilbert space just looks entirely featureless and looks almost identical to the microcanonical mixed state. Okay, so these are atypical states. And the way to state this result is that, you know, on most of the Hilbert space is entirely the space which is just shaded in some uniform orange is entirely like the microcanonical mixed state. There could be some states which stand out for a given observation, but those states occupy an extremely small volume. Okay, so this is a significant result. We'll now discuss a little bit of its significance and how it applies to the paradox. I also want to say a few more things, but if there are questions, I can take them now, and then we can go on and say a little bit more about this result. Are there questions about this?
Yeah, please go on, Tony. Go on.
Yeah. How did we get that the volume of atypical states is small?
You see, if the volume of atypical, let's say there was a volume, let's say there was an order 1 volume where delta was larger, it could not be that the expectation, you know, the integral of delta squared over all of mu was 1 over e to the s. You know, if delta is large, if delta is large for like a volume which is order 1 as a fraction of the whole Hilbert space, then the integral of delta square would be, you know, order 1. It would not be 1 over e to the s. It's a positive quantity you're integrating. And so if this positive quantity, the integral is 1 over e to the s, and if this quantity happens to be large at some point, it can only be that that's compensated by the volume factor, and that's why the integral is small.
And what's the definition of atypical again?
Atypical is just one where delta is large. State where delta is large. So, you know, it could be that, you know, you have some observation, or you have some particular observation, and from the point of view of that observation, there are some pure states which are very special. For instance, let's say we took P to be the first energy eigenstate. Okay, the projector on the first energy eigenstate, right? So let's say this is an example. Okay, then the first energy eigenstate is a very special state for this projector. You know, on the first energy eigenstate, if you measure the expectation value of P, you get 1. On every other energy eigenstate, you get 0. On the microcanonical density matrix, if you measure the expectation value of P, you get 1 over W. Okay, so the first energy eigenstate with respect to this projector is a very atypical state in that it, you know, this projector gives you 1. It distinguishes, it picks out the first energy eigenstate. But except for the first energy eigenstate, if you look at most of the Hilbert space, where it is not the case that the coefficient of the first energy eigenstate is 1 and the other coefficients are 0, the expectation value of delta is close to 0 and it's exponentially suppressed. Okay? So does that make it clear?
Oh, so the measure of these states is exponentially small.
Exactly. So, you know, in this particular case, you know, there are some states where the coefficient of the first energy eigenstate is close to 1. Those states are all atypical states because the expectation value of this particular P that you see on the screen is close to 1 for those states. But there are other states, you know, for most of the states in the Hilbert space, the coefficient of the first energy eigenstate is like close to 1 over e to the s by 2. And therefore, the expectation value of P is the same as what it is in the microcanonical mixed state, which is 1 over W.
Okay. Yeah.
Okay,
Thanks.
great. Let me say a few more things about possible confusions. And this is, okay, so let me just say, let me talk about basis versus typical states. Okay. Sometimes you will find in a discussion of pure states, I mean, this is something which is done very commonly and perhaps is, you know, one should be very careful about this. You know, one might say in some papers you will find that, let's say we have n qubits, right? Then someone might say, look, here are examples of pure states. This is an example of a pure state. This is an example of a pure state, right? This is an example of a pure state, and so on. Okay? And then someone might say, you know, let me start measuring the spin of all of these things. So there's a Z spin and there's I. This I is like which qubit you're looking at. Okay, so this I here refers to which qubit you're looking at. It runs from 1 to the total number of qubits you have. And from the point of view of all these observables, there are n such observables for n qubits. All of these states are very atypical, right? Each of these states that I've written down is very atypical. So you said, you know, if you have an observer who's sitting and who's trying to measure these n qubits, then this observer would find that all of these pure states look very different from the mixed state. Right? In all of these states, it so happens that, you know, sigma z I has definite values. And the definite value might be 0 or might be 1, but it has definite values, or might be 1 or might be -1 in all these states. Okay. But these states are examples of the kinds of atypical states we spoke about. Even though they form a basis, they're not typical states, because a basis, a typical state, is one where you put some coefficients in front of this. Okay. Into e to the I, 0.7 and 0.64. I don't know if that's normalized, maybe 0.13. Okay, and so on. And a typical state is not one of these states with coefficients 1 for one and 0 for the others, but rather it's a sum of all of these states with given coefficients. And so even though you have a basis of pure states, a basis actually with respect to this Haar measure that we are talking about occupies 0 volume in the Hilbert space. Okay, so remember that basis states by themselves occupy 0 volume. Okay? So you should be very careful when people say that, look, pure states look very different from mixed states, and they give you an example of a basis. Because remember, basis states occupy 0 volume, and in general, a typical pure state is a superposition of different basis states, and the superposition of different basis states, which is where most states in the Hilbert space are, looks very close to the microcanonical state. Okay? Let me say a second thing. Sometimes you might hear in discussions of this the phrase ETH, which stands for Eigenstate Thermalization Hypothesis. Okay. I want to emphasize that at no point in this derivation did we use any such Eigenstate Thermalization Hypothesis. Okay. Our derivation was just kinematical. A result is like, I mean, it's so simple, it's just kinematical. The Eigenstate Thermalization Hypothesis is a statement which is a more dynamical statement. It has to do with whether, if you're given a single energy eigenstate, does that single energy eigenstate look thermal or not? But our result is just kinematical and does not invoke the ETH. Okay. So the fact that typical pure states look close, and our result is that typical pure states are exponentially close to the mixed state. Okay. And this result is just a kinematical result. It doesn't even require the Eigenstate Thermalization Hypothesis. Okay. Okay. So this is the second thing, which is a possible source of confusion. Okay. Let me make a third remark.
I'm sorry. What's this hypothesis?
The second state is if you're not confused, I don't want to confuse you. You might hear often in discussions of thermalization that it's only states. It's only in theories that obey the Eigenstate Thermalization Hypothesis that pure states look the same as thermal states. But that's a statement about whether energy eigenstates look the same as thermal states. If you ask about typical pure states, and I underline the word typical here, let me underline it with something more permanent. If you ask about typical pure states, just kinematically, just from the size of the Hilbert space, they look like the mixed state, like the microcanonical mixed state. And that's just a kinematic result. It doesn't require any assumption about dynamics of the theory. And that's just what we derived right now.
Right. And what is the hypothesis?
I don't want to discuss what the Eigenstate Thermalization Hypothesis is right now. We'll discuss it a little bit later.
Oh, okay.
I don't want to go into a detour of that.
Yeah.
If you haven't heard about it and you're not confused about this, don't worry, don't get confused. Okay, so it's just a warning. If you were to hear this, don't get confused about it. Okay. Let me say a third thing. The third remark is that there are sometimes people say what one could compute the entanglement entropy. Right? So let's say one computed the entanglement entropy. So the entanglement entropy, S is equal to 0 for a pure state, and S is equal to something else, right? S is like 1 over W. S is log W for this mixed state. Right? So the entanglement entropy looks like it gives you 0 in one case and it gives you something totally different in the other case. And then you might say, look, the entanglement entropy differentiates for you pure states from mixed states. But in fact, this is actually not a statement about the differentiability of pure states and mixed states. This is a statement about the fact that the entanglement entropy is a very fine-grained observable, because the entanglement entropy is not the expectation value of any particular projector. There's a very simple proof of this. Okay, so S is not equal to it's not even the expectation value of any operator. And the reason S is not the expectation value of any operator is very simple. It's because one can always find a basis, always find a basis of states for which S is 0. If S was the expectation value of an operator, then S would be 0 for all states. Okay, and we know that that's obviously absurd, and therefore S is not the expectation value, of any operator. And what S is really is it's a function of correlation functions of any. So it's not the expectation value of any single operator, but S is a function of correlation functions. So it means that you compute lots of different expectation values, and then you compute some function of correlation functions from there. And such a function of correlation functions can indeed, take advantage of these exponentially small differences between a pure state and a mixed state, and it would give you a very different answer for a pure state and a very different answer for a mixed state. But this is a statement about physically the fact that S is very fine-grained. Okay? So the fact that S equal to 0 for pure state and S equal to log W for the mixed state, okay. This is not a statement about the differentiability of these two states. This tells you that S is a very fine-grained quantity. Okay. And you have to be very careful about exponentially precise corrections in order to be able to compute S. Of course, you might have some other prescription or some other quick trick to be able to compute S, but in the end, S is keeping track of these exponentially small corrections, and it is a very fine-grained quantity because it can distinguish pure states from mixed states that no other observable can do. Okay, so that's a third remark that I wanted to make about the distinguishability of pure states and mixed states. Okay. So far, so good. If there are questions, I can take them now. And if not, we will move on to discuss Hawking's paradox.
Hi, I had two questions. The first one is about this last thing. Because the only difference between a pure state and a mixed state is that the mixed state is has a classical uncertainty on it. But then the entanglement is a quantum property. So yes. How can, from this classical uncertainty, can you get a quantum property such as entanglement?
Sorry, I didn't understand. By S here, I just meant trace of rho log rho. This S is actually measuring the entanglement of the system with something else. So this S is measuring how mixed the system is. And if you have a mixed state, as we discussed at the beginning of the lecture, that's because the state is entangled with something else. If this room is appearing mixed, it's because this room is entangled with something outside. And this S that we, with a minus sign, this S that we are measuring is measuring the entanglement of this room with something outside. On the other hand, if this room is in a pure state, it's not entangled with anything else. So this entanglement entropy is measuring not, so this classical uncertainty that you're talking about is arising because the system is entangled with something else. And that's the entanglement that this S is measuring. And that's why it's non-zero in the case where you have a mixed state, because the mixed state means that the system is entangled with something else. And it's 0 for a pure state, because in that case, the system is not entangled with anything else. Does that answer the question?
All right. Okay. Thanks.
Yeah.
And the second thing is there some physical intuition why almost all pure states are like the microcanonical ensemble state? Why is there not a bigger spread in there?
Actually, it's I don't know what more physical intuition to give. It's kind of a it's kind of a result that's just coming from the fact that I don't have a quicker physical way to say it. In some sense, it might even be a surprising result when you encounter it for the first time. The fact that pure states look almost indistinguishable from the microcanonical state, and in fact, it's perhaps because it's surprising that it's a very simple result, but it's not always appreciated, even though it's such a simple result. I don't have a quicker physical shortcut to indicate why that's the case. If you do the computation as we did, it's a simple calculation and shows you it is the case for large systems, that pure states and maximally mixed states are the same. But I don't have a quicker physical reason for why that's the case.
Okay, thanks.
Okay.
And so then,
So could we say so the volume average that we found of the projected expectation value, that could also be defined as an expected value over a density matrix, which instead of being just a summation is like an integral,
No, see, that's not a density matrix. The thing that well, okay, so the way we defined it is not So when we are computing like, so, you know, it wasn't, we had a mixed state that we were comparing the microcanonical state to be. If you look at this delta squared, what we're saying is, here, you know, what we're saying is do the computation in every pure state and then square that and then take the answer. So it's not like we are saying, you know, first average over all states and then compute what the deviation is. That would just be 0. So notice here, you see that first you do the computation in a given pure state, square the answer, then take the average with respect to all pure states. Okay? So it's not like there is one mixed state which we defined ahead of time, which was, you know, you average over psi with d mu, and then just compute the expectation value in that. In fact, that mixed state, if you just took psi and average over d mu, you would get the microcanonical state. But that's not what we're doing here. We're saying take a pure state, whatever pure state you like, compute the answer, look at the difference, square it, and then average over all possible pure states. So it's not like there's one mixed state we have in mind for this pure state computation.
Would any
average over all pure states.
Would any of this change if we had a density matrix of this sort where we were integrating over the Haar measure, and for the matrix element we had ket ai bra ai?
Ket ai bra ai. So, you know, in this density matrix, if you, so this the way we've written this thing over the Haar measure is, you know, when you write a density matrix, usually you sum over a set of orthogonal states. These psi's, as I emphasized in the beginning, are not orthogonal. So, you know, bra psi, ket psi is not something that's orthogonal to another psi. But indeed, you could try and define some kind of density matrix by taking psi and just averaging over mu. That would be the microcanonical density matrix. In fact, that's the result, that expectation of delta is 0. You know, what we're doing here is something slightly different when we compute the deviations. It is really that you take a pure state and take the average of the deviation squared. Not that you first average over pure states and get a mixed state. I mean, that would be a trivial computation if we had done that.
Right. Okay, thanks.
Okay, great.
Actually, Suvrat, there are a couple of questions.
Okay, great. Yeah,
I think one is in this particular slide. What do you mean when you say you can find a basis such that S is equal to 0?
Oh, okay, great. You see, when you compute S, let's say you have a big system, right? And let's say I want to compute, I have like 2 qubits, right? And so I can always think of the following basis of states. This is a basis of states, and here's one more. Okay. So there's a 4-dimensional space, and here's a basis of states. Okay, I hope you can see the arrows. So it's up, down, up, down, 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 up. Okay. In this basis of states, if you ask for, let's say you compute what is the entanglement of the first qubit with the second qubit. So you reduce the density matrix in the first qubit and compute the entanglement. S is equal to 0. Okay, for all of these, there's no entanglement. On the other hand, you know, it's clearly not the case. You know, there's some other state you can write down, which is up, up, plus down, down, where S is not equal to 0, right? For this state, S is equal to log 2. And this log 2 is not 0. But if there was any operator in the bigger Hilbert space of the 2 qubits, such that S was its expectation value, because S is 0 for every element of the basis, for this one, this one, this one, this one, S is also 0 for any linear combination of the basis elements, because it's 0 for every element of the basis, right? And therefore, S would just be 0 for all states. In particular, if S had been the expectation value of any linear operator, S would also have been 0 for this state, because this is a linear combination of the state that you see here, this up, up state, and this down, down state, which is the one that you have here, right? And so this S that you're computing, which you find is log 2, is not the expectation value of any linear operator in this larger Hilbert space. And that's because you can always find a disentangled basis, as we have here.
Okay. And another question is entanglement entropy an observable?
Is entanglement entropy an observable? Yeah, it's not an observable in that there's no one-shot observation you can make which would allow you to measure the entanglement entropy, because observables are expectation values, are Hermitian operators. Okay? So entanglement entropy is not an observable in that sense, but it is a function of observables. So if you have a system and you make many observations on the system, so you know about the values of other observables, you can then compute the entanglement entropy. So you can think of it as a function of other observables. It's not by itself an observable, because an observable is a Hermitian operator. And as we just discussed, the entanglement entropy is not the expectation value of a Hermitian operator.
Yeah, I have a question.
Yeah.
When we take a deviation square and average it, we average it with taking a uniform distribution on Hilbert space.
Yeah.
Is this the reason why are we getting all typical states very close to, exponentially close to?
the uniform distribution of the Hilbert space is the natural distribution to write down. Right? Any other distribution you wrote down would be a biased distribution. So the uniform distribution is just a statement that, if you want to ask what are typical states. So it's a definition of typical is by taking a uniform distribution. It's that, I go and I find a state, and the state is some linear combination of energy eigenstates from the same range that the initial mixed state was from. And, if I were to decide that, well, I want, if there is some other process that tells you that maybe the first energy eigenstate is more likely to be produced than the second one, then indeed you would not have a uniform distribution. And then it might be the case that the results you get are different, for pure states and for mixed states. So, if your distribution was biased because of some dynamics in the process, then indeed you could have got different answers. But the only assumption we were making was that the distribution was unbiased. And that's why we took a uniform distribution.
Okay, thanks. Okay.
Great. So let me just spend.
So just to be so sorry, I have one more question.
Yeah.
So we are not talking about the full Hilbert space, right? When you're talking about this pure states, we are talking about these states which are very close to this average energy, right?
Correct.
Yes. From which this mixed state is also taken.
Yes.
So doesn't this whole calculation? I mean, what's the if I say that this whole calculation just shows that the states that I have chosen from my Hilbert space are just close to this mixed state. I mean,
but you remember the mixed state. So there were e to the, you see, so if you can ask this question again in a few minutes. You see, in the case of black holes, we do have a given energy, right? So there was some black hole which was formed which had a given energy. So what we want to do is compare, states of a given energy which are pure with this mixed state. So maybe if you ask the question again in 5 minutes.
Sure.
Can I ask a quick question about?
Yeah, I just want to say a few more things. Could you? But if it's very quick, we can go on. Otherwise, yeah.
No, go on. I can ask at the end.
Okay, great. So just give me like 5 or 10 minutes. I want to say a little bit about the application to Hawking's paradox, and then we can have a discussion as usual. So let me just emphasize. Let me just go back to Hawking's original paradox. Okay. So it should be, I hope, clear to many of you what the relevance of this result is to Hawking's original paradox. Let me remind you what the computation in Hawking's original paradox was. Right? The computation was that, look, we computed this, right? And we found that this was 1 by 1 minus e to the minus beta omega. We computed this for many other cases, right? Hawking also pointed out in his paper, as we saw yesterday, that if you took the correlators of creation annihilation operators with omega not equal to omega prime, then you would find that the expectation value was 0. So you were finding that you had these correlators of the operators with themselves, which were thermal, and then you had these correlators of operators with things of other frequencies which were different. And from this, Hawking concluded that the final state is mixed, and this was the main computation, right? This led to the conclusion that the final state was mixed. Okay. But what we see here is that this is not a valid computation. And the reason it's not a valid computation is that if I had found instead, if what the computation tells us is that pure states can be exponentially close to these mixed states. And so if I had found, in fact, that if I was to, if these answers on top were exact, like they were absolutely exact, then indeed it would tell you that the final state was mixed. But if these answers were corrected by very small corrections of this kind, where I just put in like order e to the minus s by 2, and this s is the entropy of the black hole. Remember, this is the correction that we got previously. Then this tells you that, it could well have been these answers that we have would have been perfectly consistent with a pure state. So this is perfectly consistent with a pure state. So the first, the significance of this result is that, remember, I emphasized in the beginning of yesterday's lecture that black holes are systems which have a large entropy. So they're really statistical systems. We fix the energy of a black hole when you form the black hole. You form the black hole, you have some energy, which was the energy of the infalling matter. You don't fix it exactly, and so there are some fluctuations in the energy. You could have chosen to fix the temperature or chosen to fix the energy. But once you fix the energy, let's say you fix the energy, then, the black hole in the end forms, there's some complicated process, it evaporates. And, you could get various pure states as a result of this complicated process. the fact that in this pure state you got at the end, you made some simple computations. You computed some 2-point correlation functions and you got answers that looked thermal is not only not a paradox, it is to be expected, because almost all pure states do look like mixed states. So the fact that you compute some 2-point correlation functions and you get an answer that looks thermal is not a paradox. In fact, it would have been a paradox, so it would have been surprising if you had found some answers that did not look thermal to leading order. And once again, of course, if you had exactly computed the state, if you had exactly computed and kept track of these exponentially small corrections, and you had found that the exponentially small corrections were 0, then indeed you could have said, well, now I've kept track of all the corrections and I know the final state is thermal. But as we discussed many times, the accuracy of Hawking's computation, and in fact the accuracy of our computation, okay, so let's say of our computation, was much, much smaller than e to the minus s by 2, right? Was much, much smaller than e to the minus. What that means is that the errors were much, much larger. So maybe errors were much, much larger than e to the minus s by 2. Okay, here's an example of one. Let me give you an example of one kind of effect that we didn't keep track of. In fact, many people yesterday discussed these issues of, what happens? Are you computing the full thing when the geometry back reacts and so on? But let me give you an example of a particularly simple effect that we didn't keep track of. Okay, let us say the black hole. We have these correlators. In fact, I've been a little blasé about the microcanonical state and the canonical state. These correlators are correlators with a given temperature, right? They're not actually correlators with a given whether you fix the total energy, but there is of course an equivalence of ensembles, but that equivalence of ensembles is not exact. Okay? So you could have said, let's say we form a black hole, a black hole in the micro ensemble, okay, which means you fix the energy almost approximately, or in the canonical ensemble. In fact, you expect that the correlators you get in these two states, even if you're going to say the final state is mixed, the correlators that you get in these two states are different. Okay? And observables in these two are different, and they're different by an amount that we can compute, and that amount is 1 over square root s. Okay, maybe it's a power of s if you have some other observable you're computing. But notice that this is much, much larger than e to the minus s by 2. Okay? So even this very simple fact, the fact that you could look at black holes with a large spread in energy or black holes with a small spread in energy, and these black holes would give you answers in the final correlators that were different from each other by 1 over square root s corrections, is something that we haven't kept track of. And in fact, no one has done carefully, or maybe in some very rare cases, actually of Hawking radiation, I think no one has done carefully the computation of Hawking radiation and how it's affected depending on just the spread in the energies, whether the spread in energy is small like the microcanonical ensemble, or if it's larger like the canonical ensemble. Okay? And we see, so we are not even keeping track of effects which are power law suppressed in S, let alone effects which are suppressed exponentially in S. And if we just compute some 2-point functions in the end, and which is what we did, those 2-point functions look thermal, but the fact that those 2-point functions look thermal is just not enough to argue that the final state is thermal. Okay? So the fact that not only 2-point functions, the fact that simple correlators, which is what we computed, that simple correlators look thermal does not imply, and this is very important, okay, does not imply, okay, that the final state is thermal. And so if you look at the argument that was made in Hawking's paper, and I emphasize this is the argument that was made in the original paper, is that we compute these simple correlators, we find they look thermal, and therefore the final state is thermal. That's just not true. As we have just shown, as we spent most of this lecture discussing, pure states and thermal states can look exponentially close to each other. And in fact, given that black holes are large statistical systems, the surprising result would have been if we had found that the simple correlators did not look thermal, not the fact that they look thermal. So the fact that these simple correlators look thermal is to be expected. So there's a punchline, there's a way of saying this, and the way of saying this is that Hawking's original computation is just not precise enough, to lead to a paradox. And it's not precise enough because Hawking, in fact, the computation we did could in principle be corrected, but the ray tracing computation doesn't even keep track of smaller corrections. It's harder to even correct it systematically, but this is just not precise enough to lead to a paradox. Okay. Now, there are some things that we have not answered here, and I emphasize that, of course, this is not the end of the course, and that is that one can refine the paradox, and this has been done. One can try and refine this argument, and one will come up with other kinds of paradoxes, which we will discuss. And the second thing I would like to discuss, which we have not discussed, is what about the principle of ignorance? You see, let's say the computation is not precise enough, but there was also this principle of ignorance that Hawking indicated, which came from looking at the causal structure of the space-time. It was the intuition that I emphasized yesterday that he gave for why you expect the final state to be mixed, which was that, the observer outside doesn't have any information about the interior of the black hole, except for some things like the mass and the charge. We will discuss this in the next class, why this intuition is not correct at the level of accuracy that we need. We now know what we mean by level of accuracy. We mean exponentially precise accuracy in the entropy. But if you just look at the concrete computation of Hawking radiation that was done, the fact that those correlators look thermal is just not precise enough to lead to a paradox. There are other paradoxes we can find, but this computation does not imply one. So I'm actually going to stop here because I think we're almost out of time, but I expect that there will be questions, so we can have the discussion. And just to summarize once again, the point of this lecture was to establish a very simple result about quantum statistical mechanics. That result tells you that if you're given some observables, you compute some set of observables, you compute them to some accuracy, it will very likely be in a large statistical system that those observables look mixed. But before you conclude that the real state is mixed, you need to keep track of exponentially small corrections. These were not kept track of in Hawking's original calculation, and therefore Hawking's computation just does not imply that there's a paradox. So let me stop here and we can take more questions.
Yeah, I have a question. Can I ask now?
Yeah, please go ahead.
Yeah, go ahead. Yeah.
Thanks. So if you go one slide back.
Yeah.
One more. Here you said that if the state was pure,
yes,
then these corrections in powers of S would also be present.
There could be corrections in powers of S, but all I said was to make the corrections consistent with purity, you would just need order e to the minus s by 2 corrections. There might be other corrections in powers of S that we haven't kept track of. So indeed, if you were to do some exact computation, you would find corrections in powers of S. One of these corrections would have to do with the spread of energies. So you would have to specify the initial state more precisely. And so I'm not saying that these corrections are exact up to order e to the minus s by 2. All I'm saying is that, just adding e to the minus s by 2 is sufficient to ensure that, the final result is consistent with purity. So unless you can rule out these corrections to exponentially precise accuracy, you don't have a robust enough argument to say the final state was mixed.
So just here, so that I understand, when you say pure state, you mean the state of the entire system of the interior of the black hole and the outside?
No, this is the state only at Scri plus. When we talk about the final state, the paradox that Hawking phrased was only about the final state as measured on future null infinity. Because the black hole evaporates away. So the paradox was, look, the black hole evaporates away. You get a final state at future null infinity. In this final state, we computed some 2-point correlators. Maybe you computed 4-point correlators. We found they were consistent with the thermal state. But the resolution to this paradox is that, well, that's not surprising, because in almost any pure state in Scri plus, in a large statistical system, you should have expected that they would look thermal up to exponentially small corrections. And so the fact that you found they look thermal is to be expected and does not mean that the state on Scri plus is thermal. So this state only refers to the state of future null infinity, which is the state of the final Hawking radiation after the black hole has evaporated.
Right, and the state at the future null infinity will be, Scri plus will be a pure state, but we don't know which pure state it will be, and it's probably going to be a typical pure state.
Yeah, so the assumption is, yeah, so you're right that, we don't know which pure state it is going to be. To determine which pure state it is going to be, you would have to have some accurate theory of quantum gravity that allowed you to trace from the infalling matter. If you specified the state of the infalling matter on Scri minus, you would have to work out the S matrix and determine what the final S matrix was. and you'd have to determine what the final state on Scri plus was. But the point is that, so there's going to be some state which will be determined by the details of the initial state and the details of the dynamics. But the fact that the state looks mixed is not surprising, because almost all states look mixed on, when you have a large statistical system. So this is just a consequence of the fact that there are lots of degrees, lots of Hawking quanta which have been emitted. You have this gas of Hawking radiation that has been emitted, and it has a lot of degrees of freedom, a lot of possible microstates, and so it's not surprising that it looks mixed. Of course, for a given starting initial state, there is a given final state that you could predict if you knew the full theory of quantum gravity and the full details of the initial state. But you expect, it's not surprising that you found that something was mixed.
And so in this case, we don't know the initial state and we don't know the final state, but I'm thinking there could be an initial state that would give a atypical final state that
Yes.
would have, and that state we are just excluding.
No, the statement is that there is no paradox in finding that the states are thermal. What you're finding is that indeed, most kinds of black hole collapse are not giving you atypical states. So the statement is just that there is no paradox here. You see, it could have been, and indeed it does sometimes happen. You could scatter particles and maybe they don't form a black hole at all, and you end up with some spectrum at Scri plus which is not thermal. So you could arrange for states in Scri minus with the same energy that don't give you a thermal spectrum at Scri plus, and those would be atypical states. But the point is that just the fact that you found some answers being approximately thermal is not enough to give a paradox. So the only point of this slide is to say that, we don't have a robust enough argument to lead to a paradox.
Clear, thanks.
Yeah, thanks, Jay.
So my question is, you showed that there's far more typical states than atypical states, but what in particular is atypical or typical is still operator dependent. What I mean is, like what's typical for one operator could be atypical for another, and vice versa. Right?
Yes.
So since Hawking showed that the expectation values are thermal for all operators, and here if we actually had a pure state, isn't it always possible to construct some operator for which the expectation value will be wildly different from the thermal expectation value?
Yeah, thank you. That's a good question. Hawking actually didn't show that expectation values are thermal for all operators. For instance, let's say I started inserting, I started doing correlators with lots of different insertions, with like L different insertions. This is a computation that goes well beyond the regime of the approximation that Hawking did. So Hawking, in fact, showed that expectation values were thermal for low-point correlators, for like a 2-point correlation function or 4-point. Hawking does a computation of a 2-point and a 4-point correlation function in the paper. You could go higher. But, to be able to see, if you were to ask in this room or in a typical system, what is the kind of expectation value I need to measure to be able to get all information or to be able to identify the state, you need to measure S-point correlators. And indeed, it is not the case that, so Hawking did not show that all correlators were thermal. Even for these 2-point correlators, there are corrections that were not ruled out, but there are more complicated observables, which you're right, in some cases might give you very different answers from the mixed state. But those more complicated observables, to compute them goes beyond the regime of validity of Hawking's computation. And that's because those observables do involve complicated insertions of operators. And then once again, you have to keep track of all of these corrections, even to compute the leading order answer for those observables. So it's not true that he showed that the answer is thermal for all observables. He showed that the answer is thermal for simple observables, because that's where the calculation is valid.
Mm-hmm. Simple meaning low number of insertions.
Exactly, low number of insertions of these creation and annihilation operators. Exactly.
Mm-hmm.